Okay, so for this problem, we want to show that the set of functions is linearly independent. And there's two different ways to do that. The first way to do that would be to form a linear combination of the form c1 e to the 2x plus c2 e to the negative x plus c3 e to the positive x, and then argue that this is equal to 0, which happens only if c1, c2, and c3 is equal to 0. And this is actually very difficult to do because the exponentials are going to turn into 1s when you have e equals 0, but when you have other values of x, they're going to still stay the exponential number e. So instead of doing that, another way to do this, which is kind of a brute force method, is to actually calculate the Wronskian. So the Wronskian for this is going to be a 3 by 3 determinant of our original functions for the top row, and then their derivative for the second row, and then their second derivative for the third row. And then we can calculate this 3 by 3 determinant and show that it is not equal to 0. And we will be doing a lot of this later this semester, so it's a good idea to introduce this concept now so we can kind of get some more mileage with it. So we're going to go through and use cofactor expansion to find this determinant. So the idea is you can pick any row or column that you want, and we're going to pick the top row just because it's the simplest. And we're going to expand along this row. And we're going to have the following sign matrix: positive, negative, positive, which means that we're going to use those operations to connect the terms in our determinant. So our first term is going to take our e to the 2x, and then we're going to focus on the subdeterminant created by striking out that row and that column. So that's going to be e to the 2x times negative e to the negative x, e to the negative x, e to the x, and e to the x. And then we're going to have a minus because of the sign matrix, and then we have the e to the negative x times that 2 by 2 determinant from striking out that row and that column. So that'll give us 2e to the 2x, 4e to the 2x, and then e to the x and e to the x. And then finally, we go back to plus, and it's an e to the x times that subdeterminant from striking out that row and that column. So we'll have 2e to the 2x, negative e to the negative x, 4e to the 2x, and then we're going to have positive e to the negative x. And then we can calculate all of these 2 by 2 determinants and multiply. So this is going to be an e to the 2x. And remember, this is just a forward product minus a backwards product. So that's going to be negative. And then an e to the negative x times an e to the positive x. That's just 1. And then e to the negative x times e to the positive x, that multiplies to make 1, but it's a minus because it's the back diagonal. And then we're going to have the subtraction, e to the negative x times that forward product, which is e to the 3x. And then we're going to be, and there's a 2 there, coefficient of 2. And then minus 4, e to the 3x. And then back here, we're going to have our e to the x times 2 e to the positive x, and then the negative and negative makes plus 4 e to the positive x. So we're going to have a negative 2 e to the 2x for the first term, a minus e to the negative x times negative 2 e to the 3x for the second term, and then an e to the x times 6e to the x for the last term. So that's negative 2 e to the 2x plus 2 e to the 2x plus 6 times e to the 2x. These are all like terms that can be combined, and we have just a total of 6 times e to the 2x. And we know that exponential functions are never equal to 0, so therefore we know that our set is linearly independent. And what's really important to understand here is that for this set functions, this e to the 2x is never equal to 0 for all real numbers, and that's why we can have the interval negative infinity to infinity. If you have a function that could possibly equal to 0, then of course that'd be excluded from this interval.